Okay, and welcome back. Just completed the weather briefing with Dale Eck, and I just wanted to give the online audience a heads up because we had a number of requests through Twitter and through the Ustream feed to make the presentations available online. So those of you who are not aware of the Weather and Climate Summit website, you can go to it. Let's take a look at it full screen here, and I can show you exactly how you can get a hold of the presentations from yesterday. So this is the Weather and Climate Summit. This is the home page here, and these pictures will be updated throughout the week as we have different presenters. We will put those in, and you can also take a look at the live Twitter feeds that are coming through on the left-hand side. But if you click on the agenda, and you'll see the agenda items, then you'll be able to see the abstract for the presentation, and now there's a new link on the right-hand side that says the actual PowerPoint presentation. So you can download those and get access to them, and we'll update those each evening as the presentations finish for the day. So you can have access to those. Feel free to come in and download. The main website address is www.stormcenter.com/WXCS 2012, and that'll take you to this. Also, you can click on videos, and we have also updated the presentations that we digitally recorded on the first day and the second day. They are up there, and so now you can access those. Now keep in mind, we updated those, we uploaded those to the YouTube channel, and it is the digital file in its entirety. So you might have 30 minutes of the full screen banner that gives the schedule for today. So just fast forward through that on the little time sequencing thing there on the YouTube channel, so you can get right to the presentations. We'll probably do some editing later on, but we wanted to get these things up as fast as possible. These file sizes are pretty huge as well. So that's that announcement. And also, we're going to get up Jim Ladue here from the National Weather Service, and he's going to talk about BUFKIT. And so I'll just bring this up full screen. Jim has been at the Warning Decision Training Branch of the National Weather Service, and we have a little background video for you so you can get a little bit up to speed on Jim Ladue. Let's take a look.
When severe weather is most active, a variety of experiments are conducted at the National Weather Center in Norman, Oklahoma. The Hazardous Weather Test Bed is a dedicated research space located between the Storm Prediction Center and the National Weather Service Norman Forecast Office. This year, scientists from NSSL and SIMS are participating in the 2008 NOAA Hazardous Weather Test Bed Spring Experiment and the National Weather Radar Testbed Spring Demonstration Program. The goal of these collaborative experiments is to improve forecasts and warnings for severe storms. Researchers, forecasters, and private weather company representatives work to identify and target issues of mutual interest and streamline effective experimental techniques and applications into operations. The 2008 NOAA Hazardous Weather Testbed Spring Experiment is divided into two parts. The first area is the Experimental Forecast Program, which is focused on predicting hazardous mesoscale weather events on timescales ranging from a few hours to weeks in advance, and on spatial scales ranging from several counties to the continental United States. NOAA and university researchers have the opportunity to change roles for a week and immerse themselves in the challenges of frontline forecasting. National Weather Service operational forecasters have a chance to examine emerging scientific and technological advances. Both walk away from the experience with increased knowledge of thunderstorm processes that will improve forecasts and vital forecasting tools. The other part of the 2008 Hazardous Weather Testbed Spring Experiment is the Experimental Warning Program. The goal here is to evaluate the accuracy and operational effectiveness of new science, technology, and products in a testbed setting. This program provides feedback on NSSL experimental products prior to their potential implementation into National Weather Service severe convective weather warning operations. NSSL and SIMS researchers are also involved in the 2008 National Weather Radar Testbed Spring Demonstration. The primary objective is to have forecasters evaluate phased array radar data in real time to investigate its potential operational benefits. These experiments are prime examples of effective collaboration between researchers and forecasters. The Hazardous Weather Testbed provides a unique setting for the continued pursuit of our understanding of the weather and the development of tools that help forecasters warn the public.
And all of you know that I was behind the videographer in every one of those scenes. So, actually, WDTP has been involved in the testbed in quite a few occasions, and I think we continue to be, and we benefit from that because we get to interact with the forecasters and researchers. And the great thing is that it's on the same floor and across the hall. So I want to do a little bit of an orientation here before we get in. This is meant to be a completely interactive session, and with the lights and production and the streaming and everything like that. I did notice that there's a little bit of inhibition here amongst the audience, and I'm going to do my best to make sure that you become uninhibited, but if I still see some inhibition, I need a few people that will always be there to critique whatever I have to say and to comment and everything like that. So if I can have some volunteers to start off to break the ice, that would be great. Okay, we got one right over there. And okay, Don, thank you very much. I would feel a lot more comfortable if I do get a lot of interaction back, even if it's negative. Okay.
We're good at that. We're good.
Thanks a lot. That would be great because...
Why did you ski over those people yesterday?
That was the first time that I've gotten a complaint about my skiing in quite some time. I don't know what happened, but that's how I normally ski, by the way. So, okay. So anyway, let's go ahead and move on. This is going to be a little bit unscripted. So let's see how this goes. And make sure there we go. We're going to be doing a lot of BUFKIT, but BUFKIT is really one tool in the forecasting game. And so I would be, let's say, I would be a very poor performer if I only included BUFKIT visualization without the context in which I'm looking at this. So the cases are going to be a little bit end-to-end, so to speak. And also, this is meant to be, what I could say is, this is meant for anybody, whether it's in, let's say, that is viewing this streaming or has a PC or something like that. You can actually pull up BUFKIT. You can download it. You can actually, if you have an earlier version, there's a website there with the earlier version. If you got no version whatsoever, you can actually install it right from scratch right here. All you have to do is just go to the WDTV BUFKIT. You can just Google that, and it actually works out pretty well. Up here, we have the WDTV BUFKIT page. So again, BUFKIT has been authored by Ed Mahoney, but he's gotten a lot of input from forecasters from public and private sector. And so it's really kind of a community project and a grassroots project as that. So I'll put this up here. I don't know if anybody wants to download this or type it in. Just let me know before I go too fast. Oh, I knew you were going to ask that question. This question is, does this run on a Mac? And there's a big Quidro Pro on that. It runs on Windows, but I actually have a Mac at home, and I run it through virtualization. So I have to have VMware and then Windows operating in that, and it runs just fine. And down the road, hopefully, if we have a big enough grassroots effort, we can get this on a real let's say multi-platform. It doesn't matter what platform it is, so that it can even run on an Android tablet or iPad or something like that. Okay, can I go on, or is anybody still copying this down? Okay.
Also, you can say for our online
Exactly. The online audience is perfectly welcome. This, by the way, is government software, which means that it is freely available for anybody to use. That's a pitch for government, by the way. This is your tax dollars at work. Yes. Okay, I'm going to go ahead and go on here. Okay, we have another website here. This is the cases that I'll be using today. This is actually my own, I have a website here, and I put the entire contents of what I'm going to talk about on this. And so it's basically towerofstorms.net, and that's a long story why I came up with that name. But you can then put in Breckenridge-2012. And once you get in there, you'll see a directory called BUFKIT cases. These are zipped up, and they'll look like what you see on the right here. And just have to download each case, not the .lck, but just each case here, and you can get it there. Download it, unzip it, and you can put it, and I'll show you what to do as we go on here. As I flip back and forth, probably between BUFKIT and this one, let's say the PowerPoint here. Okay, just let me know if everybody's satisfied before I go on here. Yep.
Remind the online audience that there's no technical support.
That's a good question. That's right. Dave wants to remind me that to remind you that online audience, we don't have technical support for this. Okay, so it has to work perfectly.
Do we need to download all these cases? Or?
No, you don't have to. The question is, do you have to download all these cases? And no, you don't have to. If you want to keep that browser window handy, you can do it on the fly as I go into each case. Otherwise, you can just kind of sit back and watch the show from up here. Okay, I'm going to go ahead and go on here. I'm just doing this here right up front so that you have time to download and set some things up as I introduce BUFKIT here. And let me take a poll here as in terms of at least the people in the classroom. How many of you have been here last year when Ed has talked about BUFKIT? Oh, wow. Okay, and how many of you do not know about BUFKIT at all? Okay, so John, you know about it, and you don't know about it. Okay, so I want to raise all boats up to the same water level, so I'm going to go ahead and just talk a little bit about it. But the way I'm going to do this is that I'm going to go through the cases, and that's how you'll learn about BUFKIT in a little bit more detail. Of course, the question is we get more and more data. Are we truly overwhelmed by a fire hose of information? And I think at this point, I think it may have a lot to do with we're just subjected to clunky presentation. So there's a lot of information, but if it's presented well, we can actually really assimilate it and make understanding out of it. After all, you think about it, a typical Hollywood movie is about, let's say I'm talking about an IMAX movie, is 1.5 terabytes of information. And I think when you come out of a movie like that, you're not supposed to feel overwhelmed. Except for the way they are now, that you have a scene transition every 1.5 seconds or even more frequently. But I think you get an understanding of the real context of the information, and then you have an emotional response after that movie, despite how much information is presented at you. And so that's kind of an analogy here, is that really you want the presentation to be able to give you all the information that you can possibly use. This is my example here of Avatar being probably one of the largest data streams that you could possibly imagine, being 3D, IMAX version, so forth. So I have an example here. This is a phase diagram of 1,000 to, let's say, 850 millibar thicknesses on the left, and 850 to 500 millibar thickness on the bottom. And you're looking at an ensemble prediction through 60 hours of expected precipitation types. Each dot represents a model, and as you're going through time, you see the dots bouncing around. They cluster together at first, and then they tend to spread apart as time goes on, and you can see what happens. And you see the uncertainty increasing with time. That's a lot of information right there. But if you can see what's happening, you can see what we're doing. We're actually transitioning here from a rain situation to indeterminate to a lot of snow, and then eventually the models are all over the place. And there you could say, whatever I forecast, I'm going to have a low confidence forecast at that end. But initially, you probably have a high confidence forecast. There's a transition from rain to snow. That's a lot of information presented to you right there in a sounding. Okay. Let me just ask, is anybody overwhelmed so far by the amount of data that you've seen so far?
That amount, but all the things that went into it would overwhelm us.
Ah, yes. I'm going to talk a little bit more about this coming up here. So, okay, so we talked a little bit about too much information. If you have bad presentation of a lot of information, you're in trouble. But also, if you are just looking at black box algorithm output, that can destroy expertise, and we don't want to do that either. And so we're trying to strive for a middle ground here where we are able to quickly present a lot of information, but not hide information either. And so if you can imagine, and this is not a slam against the precip type algorithms that are provided to you by NCEP or SBC or maybe by your local vendors. But this is an example of a black box. If you don't know what kind of algorithm went into producing something like the precipitation type algorithm, then you really are forced to just trust whatever model output comes out at you. So we don't want to really do that. And so the idea is that we want to actually unveil the algorithm and show you the major constituent parts into it. So here's an example of a partial, or not a partial thickness technique, but this is the Bourgeois precipitation type algorithm where we're looking at how much energy is subjected to precipitation particles in terms of above freezing versus how much is below freezing. And in this case here, we're just looking at how much is there any warm layer? And there isn't any warm layer. It's all snow over here. And I'll talk a lot about this precipitation type algorithm here coming up. But the whole idea is to actually show you what is going into an algorithm so that you understand the output a little bit better. And that's what BUFKIT strives to do. Okay, BUFKIT does display native resolution data. So it's an advantage over some other ways to visualize sounding output. I just took one method off the internet right here. BUFKIT, you might see that there's a little bit more detail here, especially in the moisture profile. BUFKIT data comes from the raw buffer model profiles, which is the actual resolution of the model data. So that's one advantage of it. Now there's a disadvantage, is that with the other technique, you could just, let's say, click on a point anywhere on a map, and it will interpolate to that point with whatever resolution it has. So each one has its own advantages. The buffer profiles come from specific stations or sites, and there's a lot of them, and most of the time they should satisfy what you need to know. Okay, just a quick overview of what the BUFKIT main screen is. I'm going to show you the displays for the BUFKIT main screen, and then the overview, or the time height. And I'll kind of swap those terms, time height and overview. So on this left here, in fact up here in the upper left, you can see what models are provided to you. And you can actually input new ones in here using a setup window. So it makes it fairly easy. And then we have a display on the left side, which represents various functions depending on what you need to forecast. If you forecast thunderstorms, or if you're interested in them, we have a cape versus shear space, we have a hodograph, we have indices, and lapse rates up here. If you are interested in forecasting fog, we have a fog display. You just click on that and you'll see a new display coming up. If you want to forecast convectively induced heavy rains, then we have a heavy rain diagram here. And so there's a variety of things like that that you can do. By the way, I did mention you can click on any one station up here and get the profiles, or you can select a map and then get the profiles that way. Okay, so the information that's provided here is going to be contextual, based on what you pick here for a tab. In this case here, it's precipitation type. And down here, we can see that we have a sounding that starts out above freezing. and we have a positive energy of 4.3 joules per kilogram. Well, what does that mean? It means that's how much energy above freezing there is that a precipitation particle has to traverse. Okay, then freezing level is down here, and we also have cloud top and cloud top temperature, which is really important. Okay, on the right side, yeah, go ahead.
Positive energy of 4.3 joules per kilogram. Is that the equivalent of the CAPE above 0 Celsius?
In this case here, for a precip type, it's the amount of energy that's above freezing. So if you have a snowflake going through and it's subjected to 4.3 joules per kilogram, most precipitation algorithms will completely melt that particle and then turn it to rain. So in fact, it's very little that it needs.
Okay, for those of you who are listening on the web, my question was about the 4.3 joules per kilogram of positive energy, and that's what he just answered.
Okay. Okay, over here on the right is a SKU-T sounding, and it's not just one sounding that you see up here. In fact, you see a whole bunch of them. And that's because we're displaying ensemble model output for this specific site. The model that, or the specific member of that ensemble is highlighted a little bit brighter than the others. So you can kind of clearly see which model you're looking at. And the model here happens to be the NAM 212. And it actually shows you a KF, which means it's using the Kane-Fritsch precipitation scheme. And the core of the model is called the NMM core. Okay, and there's two different cores responsible. This one happens to be developed by the National Center for Environmental Modeling. And then this is the forecast hour right up here. So then on the right, you have your wind profile. And in this case here, in ensemble output, you get to see all of them at once, and that might be a little bit too much. So you can actually turn on and off the ensembles right over here. If you turn it off, then you're just looking at the current ensemble member. Okay, and then finally down here we have a display where we have various functions that you can overlay. Overlays here, everything from winds to model vertical motion, that's omega, and dry adibats, relative humidity, wet bulb, etc. And there's a lake effect tab, and there's a convection tab, and then controls over here. And once we get into the cases, I'll just go through all this again, and you'll see me clicking on various things right here. Hopefully that will work out pretty well. Yes?
Back to the energy there above freezing, do you have any kind of a guide or number where the models will not melt that snow into rain? I mean, what's the threshold for that?
Okay, so I think the problem is what is the threshold in melting precipitation based on what precipitation type algorithm that you have? And it does vary a little bit. I'm going to concentrate on the Bourgeois technique. And in that technique, it's really only 2 to 3 joules per kilogram before you see a melting. It's not much. I don't know how many of you have gone up a chairlift in a rainstorm in a ski area, changing to snow as you go up. Oh, yeah, that's great. It takes, literally just only 2 towers before you see a complete phase change. And you get an appreciation for how little amount of energy above freezing you need to completely melt precipitation. And conversely, though, and I don't know how many of you have gone up a chairlift where it started out as sleet, then turned into rain, and then turned into snow. And the sleet to rain part is a lot longer. It takes a lot more energy to actually refreeze a completely melted snowflake than it does if you have a little bit of ice left, like a partially melted snowflake. We'll go over this a little bit more with the cases as we go up. Okay, so I'm going to blow you away with this diagram. I threw everything on this one here. And this is the overview. It's time height. Okay, now you're going to get a little bit confused here because the time height will actually start over here and end on the left side. So it's kind of flipped around a little bit. And there's a reason for that madness, and we'll go through it. But the reason is that it works very nicely in the mid-latitudes, because then you kind of see the systems moving in, And it looks almost, if you convert it to from a time height to a distance height, it looks like you're going from east to west. In the tropics, it might be a little bit confusing, but there's an option in the setup to reverse that timeline. On here, I have the shaded parts of the relative humidity. Okay, green is higher relative humidity. And then I have a whole bunch of lines on here. Okay, and I'll focus on these two. You see, this is the ensemble precipitation accumulation, liquid equivalent. And you see it start out all green, and then it turns blue over here. Well, it turned blue because the precip algorithm said, nope, it's going to be snow now. Or it's going to be transitioning over. And then, of course, it ends by the time you get over here, so it's all gray. Okay, so down below, this is actually the snowfall accumulations. You see them spread out all over the place. Huge uncertainty here. You can actually visualize this everywhere from, oh gosh, less than an inch all the way up to, at least in this case, over 2 inches or something like that in terms of snowfall. So you can click on and off, and just look at one of these QPFs by turning on and off the ensemble button down here. And you can also use these buttons to show you how many hours are in the time height. And then there's a whole bunch of buttons up here. Relative humidity with respect to liquid, and also relative humidity with respect to ice. That's a new update in BUFKIT. We also have also context relevant stuff here. These are contours. I click on the contour and I get a whole bunch of things I can turn on and off that are contours. If I want precip, this is where I got the precip here. If I want wind, convection, temperature, aviation, and fire weather, there's a whole bunch of buttons in there that you can turn on relevant to just those right there. And we'll keep walking through this, so by the end of the day, you'll be all experts. Okay, so here's another one. Let me just jump back 2 slides. Over here on the upper right, there's a Get Data button right there on the main screen. I click on that, and I get this dialog box here. And it has a bunch of URLs or FTP addresses, depending on what site you want to get the profiles from. And there's several sites you can get them from. In this case, I have a combination of Iowa State, of different models. I guess there's NAM. Actually, no, yeah, there's a couple GFSs right there. And then one RUC right here, and so forth.
If you're looking for a good data source, just Google the BUFKIT warehouse, and that's the Iowa State.
Iowa State is awesome.
Yeah.
Yeah.
Resource your BUFKIT data.
Yeah, there's a few good ones out there.
Warehouse. Just Google it, and it'll give you the address.
Yeah.
BUFKIT warehouse.
Penn State has another awesome site, When It Works. If it works, you have an entire map. You just click on a dot, just like Iowa State, and you can get a whole bunch of things, including the short-range ensemble forecasts and so forth. Iowa State's starting to build up theirs. They're still a little bit short on the ensemble forecasting system. They have to add more stations. They just got them around Iowa right now, at least, as far as I've seen. But they're moving. They have an archive of the rapid update cycle models going back a year. And you can click on any site and just pull it back, and that's really nice. It's very good. I'll go in that in a little bit more detail. You can enter in the lists right here. You copy them off the site, and you paste them in here using these this paste button up here. And then you can actually save this list using one of these over here, these letters, and it will create a little Word file in the BUFKIT directory. And then you can retrieve that Word file using the same letter over here. So that might be really useful once you're satisfied with a short list. Just keep that, and then you just keep going back. And so also another neat item, if you type archive up here, it turns red. And when you do that, it will archive those profiles in a separate directory so you don't overwrite them. Cool option. Okay, yeah, we're just talking about university sources. And you're getting a little bit ahead of me, that's fine. You're a good segue at least into this here. Penn State, basically all I do is search online for BUFKIT distribution site, and I get Penn State. And you see all, well, you can't really see them, but these are the models over here. 24-hour RUC archive, 4-hour or SREF archive. They have the NAM, the GFS over here, and you just click anywhere in this, and that's fine. And there's Iowa State. You just search online for BUFKIT Warehouse, and you get this site here, which again has a similar suite of models, so it should work out pretty well. Okay, I'm going to go ahead on. Another site here is the WRF Ensemble. Oh, I botched the lettering up here. That's supposed to be WRF, not WRE. But that's the WRF Ensemble. And this one here is out of WDTV. And we got 4 workstations running, creating an ensemble of models. And we run it twice a day out to 48 hours. And so we have clickable sites here, and you can put those into the BUFKIT, and it should work out pretty well. With all these sites, by the way, there's one word of caution. None of these are operationally supported, so that they can go down, come back up, go down again. And so you might want to keep all of these addresses, all of these sites handy, just in case. I noticed Penn State was down this morning. They weren't working.
They had trouble for a few days.
Yes, they have. And somebody needs to send them a nastygram to get on the ball. Well, maybe that will distract them from the real problems they have, right? Let's see. There is a suite of offices that produce their own profiles too, and you can see a map of these. I pulled this map off of the Iowa State page. It was very nice of them to pull all of these together. And the same thing goes for the NWS sites. These are not operationally supported. There's no mandate for 24/7, 99% or better returns. So again, this really is a grassroots effort. Now, if any of you are really interested in producing your own profiles, we do have some guidance available at WDTV, and we can just talk to you about it. But that should be offline. You can contact me, and we can get together with Ed Mahoney, that is. BUFKIT 11, this is a new version. This just came out in the end of December. And the one thing you'll see here, you'll see a looping SKU-T, and with what looks like a horizontal histogram in greens and purples and a couple reds on the left. And that happens to be the visualization of the relative humidity, so that the bigger the histogram or the farther right it goes, the higher the relative humidity and so forth. And so we let's say we added that histogram, and that's one example. We put in a frost point display, so analogous to dew point, and also relative humidity over ice, and also, in addition to just relative humidity over water. And that really helps, especially in the upper parts of the profile. When you get up here well below minus 10 degrees Celsius, you'll never see the dew point line match the temperature line. But the frost point you'll see match. It's got Linux compatibility, if anybody is a Linux user.
Real quickly, on the histogram on the left, you said that what do the colors represent? Because you said the values represent the humidity.
Yeah, in other words, the values, okay, yeah, the question is what are the colors? If you see purple, it's really around 99% or so with respect to water. Once you get above that to red, it's actually like super saturated with respect to water. So it kind of stands out a little bit, saying there's stuff happening here, probably a lot of condensation or deposition onto ice, snow production, that kind of thing. Okay, we have local time support and some more quality control. There was an issue with some of the ensemble members only accumulating precipitation every 6 hours. And so you have this weird histogram of hourly rates. Suddenly some of them are missing and others are there. And so we put a flag in there saying, this isn't real, it's just an artifact of the sounding. Okay, any questions up to date? Do you guys okay to go? we just got some of that stuff out of the way so we can really get onto the cases here. And so this is how we're going to do it. Okay, we're going to start off with the synoptic analysis, kind of drill in a little bit to show you the setup, at least enough to show you the setup. And then we'll take a look at some BUFKIT profiles. And then I'm going to ask you a bunch of questions. So, yep, pay attention. And then we'll do a post-mortem after that. I'll be swapping back and forth between BUFKIT and the PowerPoint. So we'll get to that here in a second. But let's go ahead and show you some of these cases. I don't think we'll have time to go through all of these. I'll present them to you right here. This PowerPoint happens to have these cases here. The next PowerPoint happens to have all the ones on the right, so I grayed them out a little bit here, but hopefully you can still see them. And for each one of these, these are cases of varying sizes. When I got through with the PowerPoint, I looked at one case and went, holy cow, this is like a whole talk in itself. But we got 4 hours, so we have plenty of time, at least so far. Okay, let me go ahead and just go through the first case here, which would be the upper left one right there, case 1. And we'll branch through. This is back in 2010 when we had winter. I was trying to find an appropriate case for this year, and I could not. It was amazing. But here you can see we have a trough, out in the west. I'll start out high. So this is the 300 millibars, and we got a nice jet coming around the trough in the southern plains out of Mexico, and then another jet, really strong one, of course, out through the northeast. And we have, obviously, the zone between the exit region of one and the entrance region of another. So as we go down, we can see that it's a southern stream trough. When we had southern stream activity, that actually got out with then the polar jet up there aloft. So 700 millibars, actually some decent cold air. We're going to focus on North Carolina over here. So this system is moving off in that direction. So we get down to 850 millibars, and you can see that the departing system up here is driving a lot of cold air down to the south. So we're setting up the stage for this system to come in and move some Gulf moisture up and over that cold air. So a classic cold air damming situation. You can see this in the surface map with the ridging going on the east side of the Appalachians, and here comes the surface wave along the Gulf Coast. So we'll move forward a little bit. This is 29th to 12. Actually, we'll move forward a little bit even more, but Oklahoma suffered a huge ice storm event on this day. And then the next day, we suffered a huge winter storm. And I mean suffered kind of loosely. Pretty much, I had a great time. Okay. Next morning, this is on the 30th, and you can see the wave is coming in. Kind of opened up a little bit, so it's moving fairly quickly. But we still have that confluence zone up there, so you know the Arctic air is still feeding in from the east side. So there it is. In fact, it's Raleigh at 925 millibars, minus 8 Celsius. Okay, let's move forward a little bit. 850, I wanted to show you 850. This is where you can see the warm air coming up and over. So there's going to be a phase change issue in this area. Water vapor, nice stream of moisture out of the Gulf, a lot of deep clouds. And you can see it's a fairly open event. You don't see much of a comma head. I think the comma head that you see in Illinois and Indiana and so forth was just kind of a leftover when the system was more closed the day before. Okay. So I'm going to do a little bit of magic here. I'm just showing you this profile, but what I'm going to actually do is we're going to go to the BUFKIT cases, and we'll go to case 1. Okay, so I'll just take those two right there. And in fact, what I think I'll do is I'll open up another, let's see right here. Oops, I did see it. I have to get used to Windows 7. I'm still stuck in XP. So I think, let's pull that out of the way. By the way, this is an excellent time for questions.
And also just to remind everybody, if you have a question, just speak into the mic. I have
Okay.
one on the front table here and one by Cindy in the middle.
Okay. Let's see. Let me make sure I pull up another one here. Okay, well, I'll just go ahead and use this one right here. So what we'll do is I'm going to put this into the, if I can find the program files. There it is. And Dave, I think you put the BUFKIT or the Breckenridge into your...
Yeah, it's right on the desktop.
Okay. That's one thing I should have pulled up here. Okay. Is it on the desktop on the side? Okay, let's go ahead and pull it up. The,
You can minimize this.
sure.
And go right to the desktop.
There we go. Okay, perfect. And we got Breckenridge is,
Should be down a little bit. Let me just bring this over to
okay.
scroll down.
Oops, over here.
Breckenridge.
There it is. Perfect. Okay. And we'll do a paste there. Okay. And I'll get more used to this coming up here, but let's go ahead and just plot the NAM. So you should see the two sites come up right there, which is in basically a comparison between Raleigh and Fayetteville. By the way, does anybody remember this case? Didn't hear my speech about spilling out the beans too early? Okay.
This is like every winter event for us.
Okay. 2010 was chock full of huge winter storms, and all of them memorable, which was great because there were also a huge number of winter storms that were not so memorable. And so I picked some of those. Okay, so I have a profile here, and which one of these tabs do you want to pick up here? Okay. Precip type. How many say aye? Not heavy precip type. Okay, immediately you see a phase space. You can see what site I picked, which is Raleigh up here. And also, you notice that my SKU-T profile kind of looks a little stretched. I don't like this, the way it's stretched, so I'm going to do a couple things here. I'm going to click on this arrow in the lower left to kind of increase the SKU-T contrast, so to speak. And I'm going to right-click on my mouse button to pull it up. I can right-click or left-click. Let's focus down here. Okay, so there we go. A little bit more detail in this case here. Let me go to overlays. There's a couple things I want to pull up. You see this button down here, it says snow growth. What does that mean? Yep.
Dendritic region about 12 below C. Crystal growth region.
Right, dendritic region from -12 to -18. So I'm going to go ahead and pull that up. And you see a little yellow bar come up there on that side, right? Okay. Okay, I like doing this one here. The model, if you notice this right down here, this button, it's probably where you can't see it. It says Bourgeois precip type. Okay, down here in the lower left, if I click that on, whatever precip icons show up in this lower left part of the SKU-T will be based on that algorithm, which is also the algorithm that you see up here in the upper left here. It's comparing the energy, the positive energy, with the negative energy down below. So if I start scanning forward.
Question real quick.
Yes, go ahead.
Should we use the Bourgeois? What's the advantages over not using it?
If you don't click this on, you'll see the precip type icon. Do you see that right here? It's a dark blue. It's probably not so easy. you'll see the precip type icon produced by the model post-processor. The model post-processor is basically the scariest precip type out of 4 different algorithms. One of them, there's a Baldwin technique, a Raymer technique, there's a couple others in there. I think some models have their own embedded, let's say, precip type scheme. Some models have an explicit, in other words, they're actually producing microphysical particles and then carrying them down. The European has one of those, and so do storm scale models. So if you pull up a rapid refresh model, it's explicit.
So this is comparing apples to apples if you turn that on.
Yes. Let me see. Let me give you an example. I just clicked on the overview. Did you see that? In the upper right, I clicked on the overview, and I pull this up. Okay. Oh, let's see here. What should we do? Oh, yeah. Let's zoom this in a little bit. This model run, by the way, is from 6Z on the 30th. So all the actions occurring on the 30th, it's a fairly short-term forecast. So I'm going to click on 24, and I spread things out a little bit. So now that you see all the action right there. And on here, I'm going to go ahead and click on snow growth. Notice I have the contour tab highlighted, and I have the snow growth. And we want to do a couple other things, but I don't think I want to overwhelm you because you can quickly turn on all of these things and you'll just get spaghetti. So let's control ourselves, at least temporarily. The one thing I do want to highlight is temperature. I'm going to contour temperature. So now you can see where it's above 0 Celsius, right? What time frame do you see it starting to go above freezing at a certain layer? And where do you see that happening? Can you read the contour labels? If you have trouble, just let me know. I'll just go ahead and help you out. This contour label here is freezing, for example, right here.
10Z or something like that?
So 10Z, it starts, okay, so right here. So we have a concern, at least at this point, that somewhere around this region we have an above freezing layer. So let's turn that off. I could turn on another, which is really useful. Notice I have the snow growth layer on, and I'll turn on the omega. Okay, now those are rather subtle red contours. Now I could turn off RH, and it might show up a little bit better. Okay, so where do you see the action? Basically, I want to see where omega intersects the snow growth region. And the more omega, in other words, vertical motion, intersects that snow growth region, the more favorable for precip, especially cold phase precipitation. Okay, so I probably want to go ahead and move this bar. You see this vertical bar here? That's basically the time at which I see my skew T right there. So that's a 6-hour forecast. There's this number 6 right up here. So right there looks like a pretty good place. We'll click it on that. Okay, now let me go to precipitation, and I'm going to add precip. Whoa, okay. That's out of control. And I'll click on precip accumulation. Okay, so the scale's a little bit off, isn't it? So I'm going to go ahead, and if you notice, there's several scales here. I have a height scale, and it's kind of grayed out. And then I have the precip hourly accumulation scale over here on the right. If I right-click on this, I can kind of bring that down a little bit so I put it in its place. And now suddenly I see another profile coming up. This is the accumulation, precipitation accumulation, going all the way up and then leveling off here, somewhere by 0Z.
Question?
Yes?
Why are you not using the bourgeois precip type on this?
I'll show you in just a second here. Let me go ahead, since you asked that question about the bourgeois and why am I not using it at this point, I'm going to turn it on and off and see if there's any differences. Do you see any differences? So there's no differences. So that's pretty good agreement. So I'll just leave it on.
So the one you're using,
I'm trying to paraphrase if you don't. Go ahead.
The precip type algorithm that you're using is the one that comes with the model output.
If I have the bourgeois turned off,
If you have the
then it
bourgeois
comes with the
turned
model output. That's right.
So for instance, from the in-car site, looking at the Ruck model or several different models where they have precip type, it's that output.
That's right. Yeah, and that is accompanied with the buffer profile itself. Okay, so this is pretty good. This is really neat. Look at this. Hope you don't mind I doing this. I'm going to turn on the RH again. Are you ready? It gets a little noisy, but you see we have saturated column, broad, deep saturated column. And at this point, you see the model omega peak right in the middle of the snow growth zone. And you notice right about that time is when we have a peak in the precip rate down below, the greatest hourly accumulation. Orange, speaking of precip type, that, if we go back to the profile, you see in the bourgeois, it's a question of sleet versus freezing rain. The profile is below freezing down below, and then we have this warm layer. And then it's pretty much saturated aloft. And so BUFKIT will display this energy diagram as a function of the positive energy that is in this warm layer, okay? And that's going to be the basically the average departure above freezing times the depth, okay, and then converted into energy. And then it's going to compare that to the negative energy down here. And you see these green, the green diagonal set of triple lines here represents the point at which we would see that change over to sleet. And notice that if I'm residing on here, okay, I have 50 joules per kilogram of, let's say, warm air right here. That's the warm air versus 100 joules per kilogram of cold air down below near the surface. So you see already the way the scheme is that it requires a lot more energy to phase change. Now here's a cool thing. If you were in Vermont in 1998, you had a huge ice storm. It was one of the biggest ice storms in history up in that part of the country. And the wild thing about that ice storm is that it was elevation dependent. Higher elevation sites, I think, escaped that. I don't know, you might have to remind me. I think that there was a certain band of optimal ice accumulations. And if you went too high, you got mostly into rain. And so it didn't work. Well, sometimes you may also wind up in a situation where you have elevation-dependent sleet versus freezing rain. And so if you have, for example, a mountain nearby, you can use this function down here. You see this right here? It says surface, and then there's two arrows. I'm going to raise our elevation by clicking the up arrow. And see you see the precip type circles starting to close in on the phase change to freezing rain. Okay, tell me what altitude I should stop. Right about there. So if I had a mountain in Raleigh at this time that was about 2,000 feet high, I would expect freezing rain on that mountaintop right there. And this kind of thing has happened a lot of times. Most recently in the Shenandoah, there was an ice storm, an elevation-dependent ice storm fairly recently, caused a huge amount of damage in the national park. And there was nothing down below. So basically, in that case, I believe it was sleet. So that's something handy that you want to keep in mind when you have terrain nearby. Or if you happen to have a very nice tall TV tower right next to your station, and the top end of that tower might be icing up even though you have sleet down below. And suddenly then when it warms up, all that ice is going to start coming down. Now that kind of scenario didn't quite happen a couple of years ago in Oklahoma City, but in 2007 we had a huge ice storm. And huge chunks of ice were coming down off of the towers around Channel 9 and Channel 4. And they were literally crashing through parked vehicles out in the parking lot. I mean, just literally, like the vehicle wasn't even there, the rooftop. You just go right through. Very impressive. So next time you have that situation, you have a big TV tower out in your... How many of you have a large TV tower out in your front parking lot? One of you. Beware. Okay. So anyway, I think these are some of the things I wanted to show, at least for the Raleigh case. So we have the freezing rain, the sleet, and you notice that the bourgeois is basically a function of either one of those two. Okay.
What happens in this depiction then if you keep going up higher above the, what is it, 5,000 feet? Does it go into rain?
Let's see what happens here. Oh, oops. It looks like we only programmed it to go up to about 4,000 feet. It's 3,500 feet. I guess we could extend that up and you'll probably see it change over to rain briefly, and then you'll see the phase diagram completely change over to a rain versus snow kind of choice.
Why is it limited in elevation right now?
Why is it limited in elevation? A certain person, the developer, has decided to limit that, and we don't know why. So I'm going to have to ask Ed Mahoney when I get back and saying, why'd you limit it?
We have his email address.
And I have it on here as well. So, okay, another thing I like to put up here, and that is the omega field. I just clicked on here. Okay, again, this is the overlays button, and I turn on and off the omega field. And it's another way to visualize the omega relative to important features like the snow growth zone right here, and also other levels down below. So I like that display, and you know what I'm going to do? I don't know if I can display. Whoops. No, probably not. I'll keep that in mind. If I actually increase this, let me see if I can increase that. Yeah, there we go. I have a function down here saying save. Okay, so I'm going to save this as an F1 so that later on I can recall it by clicking on the F1 button in the lower right. So I want to make sure I keep that.
So your save is just saving the buttons, the toggles that you've done?
All these overlays and everything else.
But not the data?
Not the data. Oops. I'm going to fat finger your display here. Okay. Let me drop that down. I can also save this one as well, so I'll save that. Okay, so let's go to Fayetteville and click on that one. And now we have an interesting situation. About the same time, look at that. The omega is off the charts. Absolutely, it's huge. So there's very large amounts of omega right there, which is quite impressive. So let's see what the overview looks like. And let me go ahead and click that to about 24 hours right there. Now take a look at this. Right now I have the model post-processor displayed. Okay. But now you see if I click on and off the bourgeois precip type, I have a difference. Sometimes you can tell why, and other times you go, The model post-processor is supposed to show you the scariest form of precip. So if the scariest form happens to be snow, okay, then it will show you as a snow if there's a tie between those. It looks for consensus amongst the different algorithms. If there's a tie between two, okay, or if there's no consensus, then it picks the scariest one. Freezing rain is the top of the list as far as scariest. So it should pick that normally here. Except in this case here, none of the post-processor algorithms had freezing rain for this time. You see it's all orange, which is sleet, or ice pellets. I turn on the bourgeois and now I get freezing rain. So that's very interesting. So let's go ahead and take a look at about this time right here where we have that difference, and we go over here and we can see what it looks like. What do you think? How many of you, without looking at just look at the sounding itself, okay? Which one would you agree with? How many of you say?
Yeah, it's got a big warm layer and not as deep of a cold layer.
Not as, yeah, so the audience is bouncing back and forth here, but some of the louder voices were going, freezing rain.
Freezing rain. That was Jim Cantori saying, freeze it, freeze it, watch it.
This is a freezing rain layer. How many of you have heard of the top-down approach for determining precip type? There's a couple nods. Okay, the top-down basically says, okay, I'm going to walk over here. I'm going to start up here at the highest point, which I have clouds, where I think I'm, got near saturation, so I should have clouds. And if that layer is cold enough, then I assume that the top of the cloud layer has got a lot of ice, and that's going to provide a cedar mechanism for everything down below. And so this looks like a case. Big negative omegas, a lot of vertical motion, fairly saturated. I should be generating a lot of precip going through this. So I'm going to go through, and then as I hit the warm layer, I look at the size of the warm layer, so forth. So I can look at it, visually, and then I see in this case here, yeah, that's pretty impressive warm nose. I mean, that's a lot more than 4 joules per kilogram or something like that it takes to completely melt typical snow. I'm not talking about hail or large grapple. So then I look at the negative area down here. I'd like to see this negative area be fairly large. I would like to see it very large to beat or turn it to precip into sleet. If I go back a little bit, let's see here. In fact, at no area do I see sufficient cold air really to turn it into sleet, at least in terms of what I think in this event here. So that's the sanity check. That's you as a forecaster going, yeah, I agree with this algorithm or not. Now, the Bourgeois is not a top-down approach. It is only looking at, basically, it's looking at the warm versus cold layer. In this case, it's a 3-layer, cold, warm, cold. In a rain snow configuration, it's a 2-layer, warm versus cold. So it's really comparing those two and then coming out with a final precip type. And yeah, it's good enough. I mean, it's a fairly decent algorithm, but it does need a little bit more verification. Yes?
Does it handle evaporative cooling or wet bulb effect? If you're, precipitating snow into very dry air down low, does it handle that?
I believe it does not. If you have a dry layer, for one thing, it doesn't handle sublimation or evaporation. Okay, and there's other issues too. It doesn't handle the cloud top temperature. It doesn't know where that precip started, anything like that. So it's a fairly simple thing. I believe the wet bulb, I'll have to check, but I think it does not at this point. But I'll check during the break. Yes. Any other questions? Okay. So in this case here, yeah, I think this is an obvious freezing rain event. But this is one way that you can, take a look at different comparisons, even though the model is saying sleet. I'm not quite sure why in this case here. Okay, so let's go back to the PowerPoint. Oh, it started right where it started. Yeah, let me just get back down here. Yeah. Like I said, it's going to be a pretty manual talk here, by the way. Keep bouncing back and forth. So, yeah, let me go back up. Yeah, there we go. Okay. So we have, I put a whole bunch of displays on this one here. The snow growth, the omega, the RH. In this case, with respect to ice, so you can actually see this area being saturated aloft and so forth fairly nicely. And you can also see with time the dry layer coming in aloft, kind of the dry slot, eroding the deep moisture and leaving just the shallow clouds behind. And correspondingly, you see the precip rates dropping off as well. So this is a kind of display that really kind of puts a lot of things together. But a lot of times you have to bounce because there's a lot of other important things to look at that would just clutter up this display too much. But I want to get you used to my clutter because you haven't seen anything yet. There's the temperature layer. You can see the onset of the cold air or the warm air aloft and the phase change down below very nicely. So overlaying temperature with the RH fields does a nice job there. Especially if I put in the snow growth aloft, you can see that where the RH is intersecting that good snow growth layer. So that's a good one. And sure enough, this is the morning sounding. This is actually Greensboro, a little bit west of Raleigh, and a little bit colder. So they were, their warm nose is a lot less, and so they were mostly rain or sleet and snow, a little bit. But you can see the nature of that. And this is the Raleigh meteogram, and you can see that it was either a snow or a sleet, and so the verification was sleet indeed. Just the models did a pretty good job, at least the NAM did. Right in that region right there. So that's phase change. It's about 11Z right in that region. I'm going to bounce back and forth again. And, okay, so 11Z is the phase change. If I went back to Raleigh and then clicked on the overview, well, there's 10Z, so it's off by an hour, but pretty decent. Not too bad. Okay, so let's go on here. I knew I was going to spend way too much time on one case, but there's so much cool stuff in here. It's got all the important things. Okay, this is Fayetteville. Remember the confusion between the two precip type algorithms. And there's confusion in reality too, actually. Started out as snow, then we went to question mark. I took this straight off the METARs, and the METARs have a question mark when it doesn't know whether it's snow or freezing rain. It has a freezing rain detection sensor on it, but it's not a very good setup to figure out the difference between sleet and freezing rain. So it's vacillating back and forth between these two types as the day goes on. So it actually, the confusion in the model realm is replicated in the confusion amongst METARs. So you see what happens there. In actuality, if we looked at the reports that the Weather Service collected that day from Raleigh and so forth, there's a great post-storm summary on the Raleigh website. Here's where Fayetteville is, and they had about a half an inch of ice, so it did verify their ice storm warning. And further north, you see that in most cases, both NCEP and Weather Service typically combine the sleet accumulations with the snow. And so this whole area up here to the north was a major snow event, an ice event, right up there. And it started out with rapidly cooling ground temperatures. So I assume the roads froze up pretty quickly up in Raleigh. Is that right? It was a mess. Okay, that's what I want to hear. So it's a good forecast. As you got further north, it was mostly a snow event. Greensburg west and up by Danville, Virginia, and so forth. So okay, so the main points. We looked at precipitation algorithms in BUFKIT. We kind of looked at the differences between the Bourgeois and the model post-processor. The one thing I did not look at, and I didn't have time, was the partial thickness technique. You want to look at it? Yeah. Now that I brought it up, it's too late to go back. So let's look at Raleigh. You want to loop it? Yeah. I knew you were going to say that. It's like a worm. I guess this is one advantage of the partial thickness technique. You can kind of visualize in a different phase space where the different thicknesses are and what it thinks is rain versus snow versus ice and freezing rain. So you can see it wandering around. Okay, and there it goes again. See that transition to snow versus IP, and then back again as it got colder again. Let me stop that loop. I can't stop the loop. Okay, it stopped. Whew. Let me go back in the critical times right there. So it's a nice handy thing. You see where you were, so you can see where you're heading. And that's the advantage of it. I guess if you don't like that, you could turn it off.
Each red dot is a model?
There we go. Each red dot is, I put it on the last 6 steps in the model in decreasing circle size to represent the past. The biggest circle being the present. Wait till I show you ensemble output. As soon as I figure out the Windows system here, I'll probably do that in a second here. But anyway, so that's what we have in terms of the main points there. the partial thickness technique was developed for the Mid-Atlantic. I mean, it was literally developed at the Raleigh office. So it should work pretty well there. Elsewhere, then you're talking about a different story. Okay, so that was case 1. Shall we go on, or do you have any questions at this point? Maybe I should ask around, see what you guys learned from this, if anybody wants to say anything. Yes?
Dr. Chick, actually, if the model has the microphysics, it will display in BUFKIT versus just the output. Is there a list somewhere of which models have the microphysics in the model, so we can go back and reference, say, okay, well, this model has the microphysics, so maybe I won't use the Vernoin or whatever.
We do have a lesson on our homepage, Warning Decision Training Branch. We have an entire course on winter weather warning decision making. We call it Advanced Warning Operations Course Winter Track. So if you search for AWOC or AWOC, or go onto our WDTB page, you can find it there. And there's actually a couple lessons on precipitation type forecasting. And we mentioned all the model processor or algorithms that the model uses. It's a, that's right.
What's the name of the course?
And it stands for Advanced Warning Operations Course.
Okay. And there's a winter course?
And there's a winter track in there. Yeah. So if you search for that, you should see it. Awesome.
Mr.
Yeah.
Cantori will be leaving us shortly because it's snowing.
The question is, are we going to include BUFKIT soundings or buffer soundings with high-res models? And yes, the answer is yes. Starting, again, a kind of a grassroots level kind of thing. Somebody who's very interested in it is actually tackling getting the buffer soundings and converting them to BUFKIT. And there's a whole suite of Quidro pros and gotchas with that, of course, which I'll definitely point to. Yeah, literally the 4-kilometer NAM is about to be launched. Penn State has actually got a display, CONUS-wide 4-kilometer output. So can you imagine sounding profiles from that? I can't either. It's data overload. That's it. The fire hose is on, that's for sure. So let's go on to case 2. Case 2 is actually just pretty recent. It's just from this December. And in fact, this is the same case that Paul showed with dual pole data from Amarillo. So let's step forward here. Excuse me. We have 500 millibar low. I'm going to go ahead and step over here. Nice intense system when we used to have those. And we have, again, a shortwave ridging out to the east, and so it's a very powerful lifting zone in between implied by this. 700, we have, this is mainly elevation dependent, but you can see pretty good warm convection field, a lot of moisture coming up. You get to 850 and you see the cold air sneaking in, just hints of it here, but again, that's the key play right there. So I'm going to focus on an issue or an area here that is different than Paul's. Here's the front is down in the Texas Panhandle. Amarillo getting heavy rain at this time, which right now is at 15 UTC, about 9 a.m. out here in these parts, 8 a.m. out here in eastern Colorado. I'm going to actually focus in on this area up here, specifically this area right here. So it's the northern edge of the precipitation shield. And in some areas, no precipitation, at least is falling to the surface, although there's probably a lot of precipitation aloft here. So we have, this is the SREF mean, SREF being the short range ensemble forecast. And I got this off the Penn State site. And this is just actually a short-term forecast. And this is precip total. And you can see, again, right along the front, this is where it's focusing. But again, the northern edge, there's an issue here. What about this northern edge? As if you didn't want to see anything, like fire hose, I'll show you a fire hose of information. This is every member of the 6-hour SREF in terms of precipitation type. And I'll just kind of summarize for you what this all means here. The shaded areas, green is rain, snow is blue, and if you see any oranges in between, that's the mixed phase, probably icing. So a lot of it is showing the icing, you know, like in southeast or southwest Kansas, right along that front end of the cold air as it's starting to go below freezing down below. And so there's variations on the same theme all the way across the board. Some of them don't have freezing rain. Some of them, it's just a rain to snow transition. Okay, so we're going to take a look at Lyman, Colorado. And here I go again, back to pulling this off. And let's go to, I'm going to get your Windows system one of these days. Okay.
Folks on the online chat are offering to come teach you Windows.
At least Dave's Windows. Okay, I got Breckenridge right here, so we'll go in here and do it the old-fashioned way. I'm going to go into my BUFKIT cases, and we're going to go to case 2. This is a simple one. I just have one sounding, and that's it. So let's go back. Playing it safe. Go to BUFKIT. Going into the BUFKIT directory and the data directory. I'm dumping the sounding into the data directory. This is where BUFKIT reads everything. So I'll paste the Lyman sounding in there. And now I'll go to BUFKIT. Okay. Oh, darn. Let's see. What did I highlight? There we go. You notice I had to click on the model. That was an SREF sounding. It's in a short-range ensemble forecast. And there's Lyman, Colorado. It pops up right there. Or if I can zoom out with the right mouse button on the map, left mouse it, zoom in on the left mouse button, and voila. Whatever the case is, there I have it. I can access the sounding fairly quickly. Okay. What do we want to look at in this case here? Let's recall. Okay. So you know what I'm going to do? I'm going to make it hard on you guys. So I'm going to turn it on to the hodograph. Okay. Let's see. 5-hour forecast. Let's go to 15Z, 16Z, and so forth. Okay, there we go. All right, I have a sounding here. Your job is to tell me whether the model is correct or not, and why. Do I have a volunteer? It's like I heard nothing but chirps and croaks out there. Go ahead.
Run this by me one more time.
Okay, what kind of, what should we be worried about in this case? What kind of precip type? It could be also whether or not we're going to get it.
Yeah, but it's gonna be snow. Yeah, I think it's gonna be all snow. And yeah.
Training Jim Cantori on Windows XP, live on the stream.
Okay. There's a time step. I have it every hour. Okay. You want to see an overview? Maybe we'll show you an overview here. And we'll go down to 24 hours. Just look at this midday period right here.
15 minutes to the break.
Okay. I knew time would fly.
Do you have snow growth turned on there?
We have snow growth. Do you see? What I'll do is I will turn on and off the snow growth. So you see it flashing?
Yeah, I see it.
Okay.
How about temperature?
Temperature. Okay. Well, let me turn off some things so I don't overwhelm you.
There's not a lot of omega.
There's temperature. Freezing is way in the lower right, so it's cooled off from freezing at all levels. Do you want to see omega? Yeah. Okay. Does anybody want to know what the Weather Service put out for a product? It was a winter weather advisory for snow. Okay.
What about your saturation relative to ice?
Oh, let's see. Let me put that up. Fairly saturated. Now, the time frame that we're looking at is just for the afternoon. So it's basically from, let's say 15C all the way up to 3Z.
Originally, when you were showing just even the SKU-T, when you go through the time, you did see a bit of a pretty good warm layer over time.
Oops.
applied. That's all cold, but that's somewhere along there.
Okay.
Where's the time?
So this is just one member of the ensemble, right? We're not looking at the entire.
I'm only looking at one member of the ensemble.
So maybe we should look at some other members.
Oh, that's a good point. Up arrow or down arrow keys. You can actually cycle through the members.
What about looking at some kind of mean for the ensemble?
Don asked about mean, ensemble mean. Yeah, you stumped the professor, see. BUFKIT does not create a mean on the fly. So unfortunately, we'd have to look at other products to see that.
Click the ensemble button, you kind of visualize a mean by where the members are, right? I mean, you kind of where they cluster, you can kind of visualize, you know, with this
Yes.
QT, kind of make one up that way, even though it's not explicit.
You can visualize it and gain a sense of what's going on right there. So you see that it does get noisy. I could turn off the omegas if you'd like, but I think you see what the profiles look like. Or you can swap through each one of these things, and you see that as well. Okay? Okay, so... All right, so what kind of precip type are we forecasting? All snow. Okay. Yeah.
We're getting questions from the online audience if we have microphones in the audience. So please grab a microphone if you have a question. That way they can hear you. Okay, so snow, everybody says snow event, right?
At the very beginning, is there potentially some lack of some cedar feeders there, so it may be like a freezing drizzle before it changes to snow?
Ah.
That's one of the comments coming on the,
Do we have a comment online about that too?
Yeah, that was my reason for asking for the saturation relative to ice. I was curious whether at the -10 and colder temperatures, if you had saturation to generate snowflakes, or whether it was all starting as freezing drizzle.
Yeah, and that's why, I mean, when you look at that sounding there, the dendritic growth region is indicated by the two hash lines there. There's, I don't know, there's enough separation there where I'd wonder if enough crystals are being generated
Yes.
initially to start it as snow.
Okay, so here's the thing. Yep, Greg Forbes was talking about that too. Do we have saturation throughout the column, even with respect to ice, which would be more likely with respect to ice than not. And this is the problem here. You see the Bourgeois doesn't know about dry layers or anything like that. It just went snow. So let's change an ensemble member. Oh, what's this up here? Warning, no ice crystals in cloud. Consider freezing drizzle. All right. Here's the cloud layer down here. It's warmer than -10 Celsius. Okay, well, you get a free trip to Breckenridge, Colorado. So, to Lyman. Beautiful and exotic Lyman. And during Vortex 2, let me tell you how many times we've stayed at Lyman. Mostly in the parking lot, waiting for convection to fire off the Palmer Divide, so we know that place pretty well. Notice not many of them are picking up there, but all of them have that dry layer and the saturated sublayer, and then a deeper cloud layer up there. You know, I could turn on, let's see here. This is RH with respect to ice, and you can see it's saturated up here, knowing that you have purple. So that's pretty good, and that dry layer right there. So, all of them have that. Let's go back to the PowerPoint. Let's see what we got. So there it is, dry layer, moist shallow layer, and then you have the big synoptic cloud shield aloft. A few model members. This happens to be the control run in the SRF coming from the, that's the spectral model, okay. And believe me, some of those acronyms that you see up there in the yellow circle on the right, I'm not even sure of, so I'll have to get an ensemble modeling specialist. By the way, the RUC model also has the same kind of configuration, a shallow moist layer, and then the dry mid layer followed by the synoptic cloud shield aloft. So low level upslope coming in on the Palmer Ridge and against the Front Range, and sneaking underneath the cloud shield up here. A If we looked at radar data, you can see Lyman indeed has freezing drizzle.
Really? Wow. That's a hell of a BUFKIT.
Does it speak to you? A new version's coming out. It's going to be called BUFKIT Siri. But the nearest radar, look at the radar data. I got 4 elevation scans, basically the lowest 4, starting with the lowest one in the upper left, and then the highest one down in the bottom left. And in this case here, you see the synoptic shield of precip coming in. You know that's snow. I mean, that's elevated stuff. But nothing's reaching the ground, so you just get freezing drizzle, and then eventually there's enough snow shield, and it changes over at around 22Z or so, or somewhere around there. And radar is hopeless. There's no radar close enough to Lyman to detect freezing drizzle. So we don't see anything there, and that's why freezing drizzle is such a pain. It is really a difficult thing to think about. This is in the news recently. I don't know if you've heard about it. This was a prison van carrying a bunch of inmates, and it went off the road northwest of Lyman on I-70, and it was a fatality collision, or not a collision, but an accident. And there were multiple accidents there. I know somebody, let's see, from the Lyman or Goodland office that was driving I-70 that morning, and she said every time she came up on a hill, the highway was a sheet of ice, and there were cars right off the road everywhere. And then she went down the hill, and the road was dry. And that's how local it was. No plows were out. The roads were not treated. And the Weather Service was expecting snow. And it's understandable. I mean, this is not an easy situation. It's a very subtle event. Freezing drizzle is a major hazard, especially if it's an onset event where it comes before the expected time of the whatever warning or advisory is out there.
So did the precip shield block, the snow shield, really even come into play at the onset?
At the onset, it did not. Okay. This is purely low-level upslope, and enough saturation that you had drizzle forming. That's right, and it was all super cooled. So, yes, it's difficult. None of the numerical models had anything. We can take a break right after this. How about that? Okay. Yep, difficult to detect, but not impossible. The models had this setup, the moisture profile, the temperatures, everything was there. It's just the post-processor and various precip schemes aren't quite there yet. And it's still, even with the precip schemes, even with our own mental precip scheme, it's hard to tell if we're just going to get low clouds fog or is there going to be drizzle out there. But with saturated descent, you can certainly expect that possibility. You know, something that you should be aware of at least. So I'm going to stop there for the break, and I think we're going to mix it up a little bit and change seasons for the second part, because I promised somebody that I would show real-time weather today.
Awesome.
Okay. Great.
Thanks, Jim. So for those of you watching online, Nancy, if you could lean just a little bit forward, and we have a little treat for everybody online, things that are going on here at Breckenridge. So while we take a look outside live, we have some snow coming down here, which is a welcome a piece of relief here for all the skiers. I just want to remind everybody, too, online that we will not have the Q&A session at 1:30 to 2 o'clock because Jim is conducting a interactive workshop throughout the whole period. So if you have any online questions, we'll try to get to those during the second part of Jim's workshop as we look at other cases and all that sort of stuff. So for now, we're going to take a break because Jim's going to dive into some other cases, and we'll be back in about 20 minutes at 12:15 Mountain Time. So thanks very much for joining us online. And oh, sorry, yeah, 12:15 Eastern Time. 10:15 Mountain Time, we'll be back. So that's in about 20 minutes. Thanks very much for joining us online, and we'll see everybody back here in about 20 minutes.